Hey everyone! So, tomorrow is a massive day. You're tackling the Level 3 OBA exam, the Brazilian Astronomy and Astronautics Olympiad. I know you've been grinding and studying super hard, so think of this explainer as your ultimate pre-flight checklist. We're going to zoom through some of the absolute most crucial concepts that pop up year after year.
You know, the universe is, well, it's literally infinitely huge, and yeah, the physics can seem kind of intimidating. But seriously, you totally got this. We're breaking down the universe into bite-sized pieces today. Think of me as your personal hype coach for the next few minutes. Take a deep breath. We're going to conquer the math and the science together, step by step.
Okay, here's the mission syllabus. We've got 4 main targets today. First, the rules of orbits. Second, stars and solar system. Third, real rocket science basics. And finally, satellites and deep space. Let's get right into it.
Initiating Stage 1, Section 1, the rules of orbits. So here's a classic OBA question to get your brain in gear. How do planets, moons, and satellites actually orbit? Like, do they just float around in perfect circles out there?
Well, that brings us to Kepler's first law, which is also called the law of orbits. The absolutely crucial thing to remember here is that planets do not orbit the sun in perfect circles. No way. They actually travel in these flattened out circles that we call ellipses. And the sun? It isn't perfectly in the middle either. It sits a bit off to the side at a specific spot called a focus. So if a test question tries to trick you with perfect circles, don't fall for it. It's an ellipse.
Moving right along to Kepler's second law, the law of areas. The big takeaway here is that a planet's speed actually changes depending on exactly where it is. When a planet hits perihelion, meaning it's closest to the sun, it feels a much stronger gravitational pull and zips around at its absolute maximum speed. But when it's way out at aphelion, farthest from the sun, it slows way down to its minimum speed. Just picture a skateboarder dropping into a halfpipe, right? They're always going fastest right at the bottom. Oh, and remember the golden rule. They sweep equal areas in equal times.
Awesome. Firing thrusters and shifting into Section 2, stars and solar system.
Here's something you've probably wondered just looking up at the night sky. Why do some stars look so much brighter than others? Is it just because they're way bigger, or maybe closer to us? The OBA loves testing this, so let's break it down.
Think about it like this. Imagine a standard 100-watt light bulb right in front of your face. It's blindingly bright, right? Now put that exact same bulb 10 blocks down the street. It's barely a tiny speck. A star's apparent brightness depends heavily on how far away it is from you. But its true power, what astronomers call its luminosity, has nothing to do with distance. A star's actual luminosity basically comes down to 2 things. Its radius, like how massive it is, and its temperature, how hot it burns. So a giant, super hot star is incredibly luminous, even if it's sitting so far away that it just looks like a dim little dot to us.
Speaking of heat and light, let's bring things back to our own planet. When you get one of those diagrams on the exam showing Earth at different times of the year, the absolute most important number to remember is 23.5. Earth has a 23.5-degree axial tilt. So many people think summer happens just because Earth gets physically closer to the sun. Totally false. Our seasons happen entirely because our axis is tilted 23.5 degrees relative to our orbit. When your half of the globe is tilted toward the sun, boom, summer. Tilted away, winter. Seriously, lock that number 23.5 in your brain.
You're doing amazing. Let's smoothly transition from astronomy over to astronautics with Section 3, real rocket science basics. So, how does a rocket actually beat Earth's gravity? Gravity is this massive, relentless force pulling everything down. How on earth do we push millions of kilograms straight up? It's all about generating upward thrust. And it's actually a beautifully simple concept based on action and reaction. Step 1. The rocket burns a massive amount of propellant, fuel and oxygen, every single second. Step 2. It takes those superheated expanding gases and blasts them straight downward out of the engines at extreme speeds. Step 3. Because it's throwing so much mass downward so incredibly fast, the reaction force shoves the rocket upward. That upward force is thrust. As long as that thrust is stronger than the rocket's weight, you are going to space.
And hey, if we're talking about going to space, we have to talk about the absolute superstar of recent OBA exams, the SpaceX Starship. It's a complete beast of an engineering marvel, and it's designed to eventually take humans back to the moon and eventually all the way to Mars. You definitely want to know your stuff when it comes to this ship. So here is a rapid-fire Starship cheat sheet. Mental screenshot time. It's 120 meters tall. To put that into perspective, that's over 3 times the height of the Christ the Redeemer statue in Rio. Massive. It runs on liquid methane fuel, which is going to be super important for making those future Mars missions work. It can carry an insane 100,000 kilogram payload. And to lift all that weight off the pad, the first stage alone uses 33 engines. 33! Keep those stats handy for tomorrow.
All right, final stretch. Section 4, Satellites and Deep Space.
Let's do a quick rundown on low Earth orbit, or LEO. A ton of satellites live here, including the VCUB that's popped up in past exams. The typical altitude is between 400 and 600 kilometers straight up. Now, because they're still relatively close to Earth, they have to travel unbelievably fast so they don't just fall back down. It only takes them about 90 minutes to do one full orbit, which means they're zipping around the entire planet up to 16 times a day. Can you imagine seeing 16 sunrises and sunsets in just 24 hours?
But obviously, we don't just hang out in low Earth orbit. Take the incredible Parker Solar Probe, for example. It launched in August 2018 on top of a massive Delta IV Heavy rocket. But space is big, guys, like really big. It took until January 2019 just to slip into its initial solar orbit. That is roughly 5 months of traveling at mind-boggling speeds just to get into the starting position around the sun.
And the crazy math of space travel really hits you when you look at the raw numbers. Specifically, 600 kilograms. The actual Parker Solar Probe, the science robot itself, only has a mass of 600 kilograms. But the rocket that carried it into space weighed 750,000 kilograms. That means the actual payload, the thing we cared about, was just a tiny, tiny fraction of the whole rocket. Almost all of a rocket's mass is literally just fuel used to fight gravity.
As we wrap up this explainer, I want to leave you with a thought. We're heading back to the moon right now with the Artemis missions. But even when a signal travels at the literal speed of light, a simple WhatsApp message from the moon takes 1.2 seconds to reach Earth. So if we want to build a real sustainable future and travel all the way to Mars, what does that kind of delay mean for our astronauts? How do you have a conversation when a simple hello takes 20 minutes to show up on the screen? Space exploration is all about solving exactly these kinds of puzzles. Look, you reviewed the orbits, the stars, the rockets, the satellites. You are completely 100% ready to absolutely crush the OB exam tomorrow. Get some good sleep, trust what you know, and remember, you're going to do amazing.